So we now want to define the concept of impulse and angular impulse. So the impulse I, which is a vector t1, t2 of a force F t acting at P, the time average of F of t and the angular impulse I angular about point A t1 comma t2 of F sorry so let me first draw a diagram. I have this point A, this is point B, so this P experiences a force F of t. This vector is clearly RPA. So the impulse is defined as t1 to t2 f t dt. This is equation 2.42. The average force of the time average force, that's maybe a better way to say this, is equal to divided by t2 minus t1. Okay, so this can be said as I of t1 comma t2 divided by t2 minus t1, 2.43, and the angular impulse t1 comma t2 t dt is equal to t1 t2 ma is rpa cross f of t to dt. This is 2.44. So this is how these three quantities are defined: impulse, the time average of force, and the angular impulse. Okay. We also must define the impulse of a moment couple. Okay, this is the angular impulse due to the force about a point A. Okay, so the impulse I of t1 comma t2 of a moment or couple moment C of t acting at Q. So let's have this point Q, and this is the couple moment for interval to t2 is 0, and its angular impulse to a t1 comma t2 about a for this interval is okay. This should be t1 to t2, and this would be C of t dt. Okay, so this is 2.45. And why is the impulse 0? Because they would consist of two equal and opposite forces. Okay, so this is something you can try to answer. Okay, please revise the concept of a couple. Okay, and see why the impulse due to this definition 2.42 should actually be equal to 0 for a couple moment. Okay, now we have another definition, the so-called instantaneous impulse. An instantaneous impulse I of t1, also called as impulsive force it is called an impulsive force, but it has dimensions of impulse. That's something you should remember. Okay, so you should not confuse this impulsive force as some sort of a force. Is said to be time t1 if the force acting at P is such that is limit t2 tends to t1 I of t1 t2 is equal to limit t2 tends to t1 t1 t2 f of t dt, and it is not equal to 0. So the difference between the impulse and the instantaneous impulse is that the time separations between t1 and t2 is negligible. So that's why you have this limit of t2 tending to t1, and this value will not be equal to 0. Okay, 2.46. So this instantaneous impulse also causes an instantaneous angular impulse. Impulse I of t1 at p causes instantaneous angular impulse angular A t1. So let me call that as same or similar definition, t2 tending to t1, A t1 comma t2, limit of t2 tending to t1, t1 comma t2 on A t dt, limit of t2 tending to t1, t1 t2, and then this would be RPA cross F. Cross I t1. Okay. Now we have to define it for a couple, this instantaneous impulse again. So we say that an angular and instantaneous angular impulse, that's also called impulsive moment, okay, with dimensions of angular impulse. Is said to act at Q at T1 if the primitive of moment C of t is such that, so this is a couple moment. A couple moment is a primitive, unlike the moment due to a force. T1 is equal to limit of T2 tending to T1 I angular Q T1 comma T2. Okay, and this value will not be equal to 0, just like we had over here. So the instantaneous angular impulse about any point is the same. So I of at T1 is the same Q T1 for any point. Okay, so this is something which you should try to answer. Why? Just look at the definition, okay? The definition is a clear giveaway. Okay. Now since because of 2.43 of equation 2.43, we have I of t1 comma t2 is equal to f average t2 minus t1. Okay, so if you look at 2.43, okay, the impulse is equal to f average multiplied by t2 minus t1. So that's what we are using over here. Okay, so a finite force does not cause an instantaneous impulse. How do we know? If f average is finite, let's say if I should write it as a vector, if f average is finite, okay, and t2 tends to t1, this would imply that I instantaneous, okay, so sorry, I of t1 will be equal to 0. Okay, so this is clearly not instantaneous impulse because it should not be equal to 0. So that's why we say that if you have a finite force, it cannot cause an instantaneous impulse. The next statement, a step force, that is the sudden application or removal of a force does not cause an instantaneous impulse. Okay, so step force, that is the sudden application or removal of a force, does not cause a instantaneous impulse. Try to answer this why. Okay, you already have a definition. I've already given an example how to check if something causes a instantaneous impulse or not. So you should try to answer this in terms of a step force. Okay, a force causes an instantaneous impulse only if it becomes infinite for an infinitesimal duration. So you can just come back to this one over here. If f average is infinite, okay, and t2 minus t1 tends to 0, then you will have an I which is not equal to 0. Okay, that is why we say that it has to become infinite for a infinitesimal duration. That will only cause a instantaneous impulse. So let's check an example. If f of t is equal to pi by 2t sine of pi t by t in the direction of E for time between t and it is 0 for time which is not belonging to 0 to t. Let's call this 1. This implies that I of 0 comma t is equal to 0 to t f of t dt. That means this is pi by 0 to t sine of pi t by t dt into E. Okay, and this, if you integrate over this whole 0 to t, this will become E hat for all capital T. Okay, so the graph of it looks like this. Okay, so f is a sinusoidal function. Now f can also, the magnitude of f, okay, can also be like this. Okay, so these are all sinusoidal functions. Okay, it's just that the time, this periodicity will keep on changing, but since this result is valid for any capital T, okay, this will be true, so even for this T. So I hope you can see what I'm doing. I'm making T smaller. T becomes smaller, but the area under the curve will always be equal to 1. Okay, because you have 1 over here. Okay, now if you take a limit such that t tends to 0, okay, in that case f average tends to infinity, but okay, because you already know what f average is, so the impulse in this case, this is t, and this is the case for t tending to 0. Over here f of t would be like this and it would be infinity. So this graph which you see will keep on shrinking as t becomes smaller. So f average will be tending to infinity, but I of 0 to t has still the value. What is the value? 1e, okay, because of this. Okay, So this is the case. And you know that f average, so this is equation 2.43 is equal to I divided by T2 minus T1. So this interval is tending to 0, okay, because this is between 0 to t. Let me do that. So t minus 0. So since t tends to 0, this entire thing should tend to infinity, okay, and hence this tends to infinity, but this will still be equal to 1, okay, because this result is independent. The value of this I is independent of the duration t. So even for this limiting case t, the value will only be equal to 1e. Okay. 1e at t equal to 0. So if you have, say, the impact of bodies are modeled as using impulsive forces. Okay, say like the kick on a football and so on. Okay, those are all impulsive forces. A large amount of force acting for a very short duration. Okay, so now we can move ahead to our impulse momentum relations. Okay, so one of the statements now, the importance of which will be seen in the few minutes to come, that all defined entities, okay, in this section are with respect to an inertial frame. We will see this in a few minutes. Perhaps you should try to catch why this is true. Okay. So if you have this f equal to MAC, okay, this requires two integrations with respect to time. Okay, so one of them will be giving velocity, the other will be getting to the position. Now if f of t is known and vc of t is required, sorry, if the velocity of the center of mass is required, then you would require an integration of f equal to MAC. So this requires one integration of f to MAC. So let's see how the impulse momentum relation will be useful in this pursuit of finding Vc, so which is the velocity of the center of mass. So the impulse, as we know, is t1 to t2 f dt is equal to t1 to t2 p dt. This can be written as p of t1 of t2 for dp. Now you can see that we have written f is equal to p dot, okay, and that is an Euler's axiom, and that is only valid in an inertial frame, hence justifying this statement in green. Okay, the Euler's axioms are only valid in an inertial frame, hence this was defined like this. Now you want to write this as t1 comma t2 is equal to f average t2 minus t1 is equal to p of t2 minus p of t1, just by integrating this. Okay, this is written as delta p equal to m into delta vc equal to, if you want to write it for the whole body, mi delta vci. This is 2.48. Okay, that is the impulsive of external force. So Euler's axioms are only about external forces, though it was not needed, I still wrote it, equals the change in momentum. So you should look up the example of a pile driver hammer. Okay, now when I say look up, you should look up on the internet how this works, perhaps with a video, just to understand how a pile driver helmet works. Okay, so for a pile driver hammer, the impact interval t2 minus t1 is kept small to have large FAV. Okay, similarly devices meant to prevent injury like a helmet or a seat belt in a car okay are designed to increase this time t2 minus t1 okay so as to decrease this F average. Okay, so you can always also see how a helmet or a seat belt prevents injury prevention in the case of an accident. Now this 2.48 is valid for, so you see we have used this index notation. Okay, so this is actually hold on, let me just okay, so this 2.48 equation 2.48. So with the index notation, it would mean that if you have this whole body of mass m and one part is m1 and it has its center of mass moving at vc1, and the other is mass m2, its center of mass is moving at vc2, and so on. So you can just add up all of them. Okay, that's how the index notation has been used over here. So this equation 2.48 holds for Cartesian coordinates, as ax is equal to vx dot, ay equal to vy dot, and az equal to vz dot. So along the x direction, okay, since impulse is a vector, so it will have these individual components, and hence I don't have a vector sign, okay, because I am clearly this is clearly a scalar quantity. It goes from t1 to t2, and then you have fx into dt. So fx average, okay, into t2 minus t1, and this quantity, if you just look at what is there in 2.48, is equal to delta px, okay, or m delta vcx, or mi delta vcix. Okay, so all in the x direction. So such relations are not valid in ER, E5 and En, okay, because this is not actually true over there. As you know, AR is not equal to VR dot, and A5 is not equal to V5 dot, and AN is not equal to Vn dot. So this was necessary for this 2.48 to work. Okay, like basically converting this to over here. Okay, so let's write, say f is made up of three components, f, phi and fr. So the first integral, what did we do over here to the first integral? You see, okay, f equal to mse was there, then we wrote the first integral. Let's see over here, that's much easier, I think. Okay, over here, so we wanted to use the impulse momentum equation because the first integration of fx, okay, we would have got this velocity of the center of mass in the x direction. But try doing that for the cylindrical system. So f phi would be equal to m a center of mass in the phi direction. This would be m. Now the acceleration, if you recall, is written as this rc square phi c dot. Okay, please check how this acceleration in the phi direction is given like this. We had done it quite earlier in this course. Now if you try to integrate it, a first integration, see what happens. Let's say rc goes on this side, so we'll have m into delta into RC square phi C dot. Okay, so delta for this quantity in the brackets, this would be RC F phi dt going from T1 to T2. This is equation 2.49. Okay, now if F phi is 0, this would mean that the change in this RC square phi dot C will be equal to 0. This implies that RC square phi dot C is constant. Okay, this implies that RC into VC phi is constant, because VC phi can be written as this RC phi dot C. Okay, so this is what we get now, and that's the reason we cannot have this relation being used in any system other than the Cartesian coordinate. Okay, reason proved with an example. Okay, okay, okay. Now we want to write the instantaneous impulse at T1, so we'll take up equation 2.48. Instantaneous T1 equation 2.48 gives us I at T1 is equal to delta P. Okay, this would be P into T1 plus minus P into T1 minus. Now this quantity will be V C T1 plus minus Vc into T1 minus. Okay, this is equal to Mi Vci T1 plus minus Vci Ti minus, just like in the previous cases. So this is 2.51. This also means that the momentum, the velocity of the center of mass, and the velocity of center of mass of the individual parts, okay, they change instantly. So because T1 plus and T1 minus are just immediate instants of each other, okay, and they do that without change in position, since VC F is finite. Okay, now let's see this RC of T1 plus minus RC of T1 minus is equal to limit of t2 by t1, t1 t2, vc of t dt equal to limit of t2 tending to t1 vcf t2 minus t1. This is equal to 0. Okay, so that's the statement which has been written, and this is the mathematical, that this changes without change in position. Okay, and that you can see that there is no change in the position because of this. Okay, because this is finite. Okay, t2 minus t1 will be tending to 0, and hence this quantity becomes equal to 0. So there's no change in the position. And lastly, if I of t1 comma t2 is equal to 0, okay, then equation 2.48 implies 2.48, if you can see, is this. So if this impulse is 0, then this equation implies that the momentum is conserved. Okay, since delta p is equal to the impulse. So let me put that in words, and even the individual parts, they will also have the same momentum, so the summation of which will be the same. So then equation 2.48 implies conservation of momentum. Okay, so P of T2 equal to P of T1, or Vc, since the mass is not changing, equal to Vc of T1 and Vc of I T2 Mi Vc of I T1 2.52. Okay, so in this particular case, when I say in this case where momentum is conserved, essentially in the internal forces cannot change the velocity of the center of mass, though the individual velocities can change, though velocities Vci of different parts can be changed. If a particular component of impulse in some fixed direction is 0, okay, for example, where did it go, say in the x direction, okay, if impulse in the x direction is 0, then it would mean the corresponding component in the x direction, which is px, this will remain conserved. Okay, direction is 0, then the corresponding component of momentum in that direction is conserved. Okay, so if Iy of t1 comma t2 is 0, then Py is equal to mvcy equal to mivcy, sorry, I is conserved. So we have angular impulse moment of momentum relations. Let's discuss this. Just like we had the impulse moment relation, we now want to have its angular impulse moment of momentum relations. This is just the angular perspective to what we have just studied. Okay, so just like last time, we have all entities in this section. Are with respect to an inertial frame. So if A is a point such that the acceleration of A at time t is 0, and obviously this is in with respect to an inertial frame, okay, or A is the same as center of mass, okay, or the acceleration of A is along AC, okay, for all times, then MA is equal to HA dot. This is something which we had shown earlier, okay, under what situation this can be true, okay, and this was actually done after equation 2.36, okay, so let me just write that over here, equation 2.36. so please pause the video and go back and check this fact and then come back. Okay, so this yields the angular impulse and moment impulse relation. So let me say I angular A t1 comma t2 is equal to t1 comma t2 HA t1 HA t2 dHA. So I angular of A t1 t2 is equal to HA of T1 minus as a vector HA of T2, sorry, T2 minus T1, T2 T1 delta HA, okay, 2.53. And as you know, to write MA as DHA, this required us to be in the inertial frame because we are using one of Euler's axioms. Okay, so that's why we had to do all this in the inertial frame. So please check this derivation, okay? Only then all this will be clear. Now these relations imply two things in words, okay? We should also have the ability to say all this in words. The external angular impulse about A equals the change in the moment of momentum HA. That's the first. And the second is that if I angular A T1 comma T2 is equal to 0, then equation 2.53 implies that HA is conserved. Okay, so the moment of momentum is conserved. In the earlier case, if you remember, if the impulse was 0, then the momentum was conserved. In this case, if the angular impulse is 0, then the moment of momentum is conserved. Okay. So the same results hold for if the, say, angular impulse about a point A in a particular direction is 0, then the moment of momentum along that direction is only conserved, not in the others. Okay. So we can write it in words, since the results 1 and 2, okay, just above you can see, are valid for a point A fixed in I if a component of I angular A is T1 comma T2, a component along a fixed direction, in I is 0, then the component HA in that direction is conserved. Okay. And similar to the case as the previous section, we can also make this, let me put that in red so that you can derive this by looking at previous section. If an instantaneous angular impulse acts at t1, then without change in position, there is an instantaneous change in moment of momentum about center of mass C, about a point O fixed in I. And about any point A in arbitrary motion with respect to I, whose velocity does not change arbitrarily at t1. So A can be any point, either a material point of the system or a point outside S. Okay, so for proving this in red, you have to use this thing. Okay, so please read this carefully, try to use this knowledge over there, because only doing this will confirm whether you have understood the previous argument or not. So this is a very good exercise for you to do yourself. Okay, it should exactly take the same amount of lines, perhaps a few terms more, but the ideas are exactly the same. So in this case, the angular I angular C at T1 is equal to delta HC, okay, and I am at O at T1 is delta HO, and I am A at T1 is delta HA. Okay, so this is 2.54. So this is the angular impulse moment of momentum equation. Okay, so this result is valid. Since positions of C, A and VA remain same. Delta VA is equal to 0. Let's see that in a figure. So this is C I of t1, sorry, I of t1 and C at t1. Now this point A is somewhere over here. This is RCA. Velocity of A at t1 plus is the same as velocity of A at t. Okay, so it's the exact same argument which we have used in the previous section. So please check that, and this ensures that there is no instantaneous change in the velocity. This ensures that. Okay, so delta of HA will now be delta of HC plus RCA cross MVCA. Now recall where this has come up. So writing this thing as HA. Remember, there were some quantities which were written in terms of the center of mass. Please go back and check. This would be H delta HC plus RCA cross M delta VC. Okay, now okay, delta HC, sorry, this should be written as I angle C about T1, okay, because of this, plus RCA cross I of T1. This quantity is I of T1, and this can be written as I angular A T1. Okay, so this is proved. Now I angular B about B for T1 is not equal to delta HB for any other point. Of system or otherwise. See, there are a few restrictions about this point A. Okay, about any point A in arbitrary motion I whose velocity does not change arbitrarily at t1. Okay, and that this is that part. So it cannot just be written for any point B. Okay, so it is only for a specific point A which satisfies those conditions, because they are used in the proof which we have just seen. Okay, okay, and the last sort of topic over here, at least, which is somewhat related to this, is the so-called work energy relation for center of mass C of any system. So let's define W star as F dot VC is the, sorry, W dot star as the power of all the external forces, or of all the external forces, as if acting at C. Okay, so this is 2.55, and similarly define Tc as equal to half into mvc square in the I frame. This is the kinetic energy, okay, as if all mass is concentrated at C, which is the center of mass. So this is 2.56. So we can say that in general W dot is not the same as W dot star, and Tc or T is not the same as Tc dot. Okay. You can check back the definitions of W dot and Tc just to confirm that in general it won't be true, because there are some additional terms. Please check those quantities. So okay, now F, as we know, can be written as MAC of I. This is okay. This implies, now we dot this with VC on both sides. This would make it MAC dot. So I should just write in the I frame. This is all in the I frame. Okay. This means that I can write this quantity as d by dt of half into m vc of I dot vc dot I frame. Okay. So if you apply the chain rule, one of them will become an acceleration, the other will remain the velocity, and so on, and a dot b is equal to b dot a will be used. So this can be written as d by dt of half into m vc square in the I frame. This entire, because this derivative is taken in the I frame, time derivative. Okay, that's why this I is coming over here again. And this is nothing new. If you recall, we always write the time derivative with respect to the I frame or any other frame which is specified. So Tc dot is actually equal to W dot star. Okay, because by doing this, this is actually equal to W dot star, and this is equal to Tc dot, sorry, Tc. Okay. Now this also implies that now Tc2 minus Tc1 is equal to W star going from 1 to 2. This is 2.57, and we want to write this in words. How would we say this? So Tc1 and Tc2 are the values of Tc in configuration 1 and 2 of the system. Remember, this is Tc. Okay, it's a kinetic energy as if all mass is concentrated at C. And W star 1 to 2 is the work done from configuration 1 to 2 by external forces, as if they were acting at sea. Okay, just by this definition of W star which we have over here, W star dot. Okay, so now this work energy relation which we have written for the center of mass, energy relation is not applicable when instantaneous impulse, impulsive loads act, since AC in that case will tend to infinity, and this proof will not be valid. Please look over here. If you have this quantity as tending to infinity, you cannot write it in this particular form. Okay, you cannot write it like this. Basically, you cannot write AC of I is equal to VC dot I if AC tends to infinity, because you see this is a differentiation, okay, and integrations, so it can only happen when you have finite quantities, not infinite quantities. Okay, so this should make sense now. So the proof of this 2.57 requires AC to remain finite. Okay. Okay, so you may be already familiar with the concept of friction, but we'll be briefly discussing this over here as well, so that if there is any lack of clarity, that should be sorted out here itself. So you are already aware that if you have two surfaces in contact, then there is a surface force. Okay, say this is a surface force, and it has two components. One is normal, the other is friction. Okay, so you are already aware of this, and this friction is what we want to learn about over here. Friction, normal. Now what does friction do? And this is important, hence I am writing. Friction obstructs the relative sliding between the bodies. So its direction on body 1 is opposite to the possible or existing relative velocity of point P1 of body 1 relative to the point P2 of body 2. So if this point is P1, this is body 1, this is body 2, and this point is P2 over here. So the direction uh, of friction on body 1 is opposite to the possible or existing relative velocity of point P1 relative to the point P2, okay, with which it is in instantaneous contact. So that's the part about direction, and since the bodies are always pressing toward against each other, the normal reaction on body always points into its interior. So the normal reaction will always be into the interior. Okay, for this is body 1 and over here it will be body 2. Okay, now if there is a slip, between two bodies, then friction will cause an energy dissipation. Okay, partially as thermal. So the energy will go into the environment because of this friction. Okay, now the loss of energy is definitely there, maybe high. Okay, so it's claimed that it's 20% in automobiles. So if you know how automobiles work, you should perhaps know what are the possible places where friction acts and causes this loss of energy. So this is definitely a problem because the energy which you are supplying, part of it is getting dissipated. So the wastage is more, and hence the overall efficiency of any machine will be less. Okay, so this is definitely one problem. But the bigger problem is that of wear. Okay, so what happens is that when two bodies slide or slip across with respect to each other, then there is this wearing which happens, wearing of surfaces, and this is something which is actually of a bigger problem. Okay, because it leads to failure of components. So you may have heard of the word worn out. Okay, so this comes out from this that the surfaces have worn out, and then there is a uh, need for worry because we can have some sort of a surface failure. So this is also a bigger problem, and it is not really desirable in many places because of these two reasons. One is the energy dissipation, the other is wearing. Okay, but it's not always useful. Okay, sometimes friction is required. So let's call it this way: many a times friction is undesirable. So you should look up each of these examples which I am writing over here. You have to see what these things are: bearings, power screws, gears. Okay, and then see where friction acts in these cases, which will cause either a dissipation or wearing. Now in sometimes it is needed. Friction is desired, and when I say desired, it includes the dissipation of energy into heat. Okay, for example, brakes, because of the friction during the action of brakes, yes, energy gets converted into thermal energy, but that is beneficial. Okay, we want that to happen. We want the friction so that like the vehicle or the cycle can be stopped. Okay, now at this point you should also be learning about a newer concept on yourself, so please do it. Something called a regenerative braking in electric vehicles. please try to understand what this is and how it helps to increase the range of an electric vehicle because of this. So please learn about what regenerative braking is, and you will always hear that the range is like how many kilometers you can drive in a vehicle is always greater in cities compared to that of the highways. Okay, that's reverse of what we have in petrol, because there's a lot of braking which happens in cities which doesn't really happen on a, say, a expressway, and that increases the range somewhat. So please look up into this term. Okay, so if the friction between dry rubbing solids bodies is called dry friction, so let's give that the friction between dry rubbing solid bodies is called dry friction. Okay, we will not be learning about fluid friction over here. Okay, perhaps that is something which will be done later. It exists, but we are not doing it right now. Okay, so that we can just focus on some things in a greater detail. Now, what is the cause of dry friction? Say any two surfaces which look like this, if you really focus using a microscope, okay, it will look like this. Okay, so let me show that over here. So there is an interlocking between two surfaces at microscopic level. So a surface which looks smooth like this, if you take up a microscope and see it, these two surfaces will look like this. And because of this, when one of these bodies try to move with respect to the other, because of this interlocking between these two surfaces, there will be a prevention of this, and that is considered as the cause of dry friction. Okay. So when motion happens despite this, perhaps you apply a large amount of force, then what will happen? Some of these surfaces will actually wear off. Okay, so these troughs and peaks which you see will become somewhat worn off like this. Okay, so there will be wearing of rough surfaces. Okay, so experiments have shown two things. One, that frictional force at instant of impending slip of impending slip, meaning the instant at which slip is just about to happen. Okay, the frictional force at the instant of ending slip is proportional to normal reaction. Okay, remember this had two components, one was normal, the other was friction. So that's what we mean. And then this was the first observation. Secondly, you will have this that the friction force is independent of surface area. Of contact. Now it's a question to you, can you think of experiments in which the above two observations may be made? Please take your time and think about this, okay? So if you have a friction force during continued slip, the earlier was impending slip, okay? This is continued slip. This is called kinetic friction. Is less than that at impending slip. Because some interlocking, at least some, okay, at least some interlocking perturbations or perturbations have sheared off. Okay, since they have sheared off, their ability to restrict motions will be reduced, and hence this friction force will be less. There is no time to form new bonds. Okay, so friction force is normally independent of the speed with which these two contact points are sliding with respect to each other. Okay, so by and large this is true, and then it also depends on the local temperatures which are there and the adhesion between the contacts and so on. Okay, so a lot of other factors affect the magnitude of the friction force. So let's first now take up the axiom dry friction. Or Coulomb friction. Okay. So if we take up two bodies, like what this is body 2, okay, and over this I place this body 1. So the hidden edges are shown with this dotted line. Okay, so this is body 1, this is body 2, and then the point P1 is say shown somewhere over here. P1, and then you have this body 2, same point as P2. Okay, I'm showing it like this, but it's the same point. Okay. So at point P1 of body 1, which at time t is in contact with P2 of body 2, the normal pressure and the tangential friction components P and tau, okay, so the normal pressure and tangential friction components, there's clearly this force F which is also acting on this body 1 of so this is called P, this is called tau, component of surface force density. Okay, so this is a clearly distributed loading, okay, surface force density, and then this magnitude of P will be P, magnitude of tau will be tau. They are as follows: for no slip between P1 and P2, we have tau is smaller than mu s P. This is equation 2.58. So tau is found from equation of motion. That means you must somehow try to measure the acceleration of this in the direction of tangential direction, and then you can use the equation of motion to find this. The second possibility is that there is a impending slip between P1 and P2. In such a situation, the friction will be equal to mu s P. Okay. And this we have learned that, right, it was supposed to be proportional to the normal component through the experiments, which you should have thought by now. Okay, this is 2.59. So this is a linear proportionality, and tau is directed opposite to the direction of impending slip of P1 relative to P2, that is tau is opposite to the component of acceleration of P1, P2 at the given time plus, okay, just the next instant in the tangent plane. And the last slip between P1 and P2, sorry, you will say that tau is equal to mu k, the kinetic friction, 2.60. Okay, and in this case tau is directed opposite to v p1 p2, the relative velocity at t, okay, and mu s and mu k are both greater than 0, are called the static and kinetic. It's also called dynamic, but I'll just use the word kinetic coefficients of friction with mu k is smaller than mu s. This mu k smaller than equal to mu s is there because of 2.59 and 2.60 and the experiments. So tau will be smaller in 2.60 compared to 2.59 only when mu k is smaller than equal to mu s. Okay, so in the limiting case it will be the same as mu s, but in general it is smaller. And these, what we have written like mu k smaller than mu s, smaller than equal to mu s, are these mu s and mu k are independent of pressure. Okay, the normal component of this surface force density, which is the pressure. Okay, and it is independent of the relative velocity. Okay, and obviously area of contact. So you must have already done problems before where you do not really know in which direction friction acts, and then what you do is you just assume a motion, a relative motion, and friction acts opposite to that intended motion. You apply that, and then you finally check your answer. If this assumption that your motion which you had assumed was correct and the friction which you had assumed was correct, the answers come out to be positive based on your sign convention. And if for some reason it's negative, then you know then it actually acts in the opposite direction. Okay, so you have already done that and you will continue to do that. So there is no other method. Okay, there is no other method to do this. The only way is doing it in this way. Okay, now perhaps I should draw this over here. So if I draw this body 1, this point P1 is over here, it will have this component P and it will have this component tau. Okay, for this situation. Okay. So if you now have this situation which looks like this, so you have body 1, then you have the cylinder kept over it. Okay, should just draw it like this. So if the two bodies, the contact between two rigid bodies is idealized as a line. Okay, in this case, okay, the contact between these two, the cylinder and this plank, is idealized as a line, then equation 2.58 to 2.60 hold with P meaning P and tau being normal and tangential components of the line force density, okay, respectively. So for example, in this case, let's take up body 1. Okay. We'll have this P acting like this, and perhaps this is a normal direction, and tau, I'll show it with a different color, tau will be acting tangentially. Okay. Now just to confuse you further, okay, since we are not really providing any proofs, I mean when I said that mu is independent of the P over here, okay, these mu s and mu k are independent of P and the relative velocity and the area of contact, I didn't provide any proof. I mean I just said that this is like that, and you had to think of certain experiments for this. But in many cases it works, like especially for metals, but then there are materials when it's not actually true. Okay, so for metals the axioms are satisfactorily valid. Okay, but say for rubber, mu will decrease with increase in P, so it's not independent. So you should, as you should know that the mu which you have, say uh, mu s or mu k, they are surface properties. So please don't look up, say a certain table and then say that the friction of this friction coefficient for a rubber or a metal is like this. It depends on what surface you are contacting it with. Okay. So you should, when you look up, you have to look up a combination of uh, friction coefficient between body 1 and body 2 in contact. Okay, so this is what you should be looking up. Okay, now if you have the P in this direction and say tau in this direction, you will have a resultant Q. This is in the direction N. Say this is the resultant Q. So this tan theta will be equal to tau by P, the magnitudes only. Okay, and the limiting value of theta for no slip. Okay, so for example, you want to say that tau is equal to mu s of p. This is the limiting case. Okay, when tau is equal to mu s p, then it's a limiting case in which the no slip will happen, because beyond this value the slip will happen. So this is perhaps the maximum value. So the limiting value of theta for no slip is called, let me not use phi, let me use theta s. Okay, limit of no slip is called the angle of static friction, theta s. Okay, so tan of theta s is equal to what? Mu s p by p equal to mu s, and tau by p will be smaller than equal to mu s. Okay, this implies that tan theta will be smaller than tan of theta s, and this implies if you are between 0 and 90 degrees, definitely theta is smaller than theta s. Okay, so this is something which one should keep in mind, that theta has to be smaller than theta s. So if you have a friction force, if friction force tau is equal to 0 for no slip, impending slip and actual slip, that is mu s is equal to mu k is equal to 0, then the contact between these two bodies is defined as perfectly smooth. On the other hand, if friction force tau is very high, so mu s for example may tend to infinity, and slip between contacts is not possible, then this contact is defined as perfectly rough contact. Okay, so both of them are sort of extremities. One of the things which you should actually mark with a lot of importance, that the coefficient of friction perhaps you knew many of these things before, okay, know all of this beforehand, but I have to mention for the sake of completion, the coefficient of friction for a highly ground and polished surface so physically smooth, okay, is more than an unground surface with more waviness. Okay, waviness means the surface looks like this. So this is a physically rough surface. So this is due to greater adhesion. You should know this word adhesion from the word adhesive. What does an adhesive do? Okay, adhesion for the former as surface elements are much closer over most of the surface. Okay, please draw the surfaces. Draw these two cases and see in what case the adhesive force seems to be greater than the other. Okay, so we have already learned before that for any force system, the simplest resultants of the distributed contact force system and the distributed frictional force system are wrenches. Okay, so that will also be true over here. So simplest force system due to distributed contact force is a wrench. Okay, so at this time you should go back to where we had discussed about the uh, motion of a motion of a bolt on a fixed nut. Okay, there you should be able to see this. Please don't move ahead behind me. I am going fast on this section just because I assume many of the things would be known to you. But if you are not able to visualize these things or understand them, especially the things written in red, then you have to pause the video, go back, understand, and come back to this video. Okay, please don't ignore any of these things over here. Okay. So if you have, say, a plane contact, let me just draw this. If you have this plane, so this is direction E, this is direction N, okay. So this is the solid kept, and then there is a force P acting on this. So if I model this contact surface, this surface, okay, I can take a small area over here. So this is area A, this is clearly area dA, and I will have the P. So on this area it will be PdA in the direction N. Okay, and then I must also show the friction. That will be minus tau dA in the direction E. Okay. Okay, so if you have, say, this is an example which you already know. If you have a block like this, it's on a plane surface, then the weight, okay, sorry, see, this is the normal force, this is gravity, you have P, and then you have F, something like this. So if the contact surface of A is plane, surface A is plane, then the direction, if this is the diagram you should look, then the direction and sense of tau is same at all points. Okay, so in this case you will have the normal force N will be a resultant over this area PdA. Okay, just look at this diagram for the small area dA, and you will have the resultant frictional force will be tau dA. Okay, and they have some relation. For no slip you will have F is smaller than mu Sn. For impending slip you will have F equal to mu Sn, and then for slip it will be F equal to mu Kn. Okay, this is equation 2.62. So most often this F is not equal to 0 for no slip. Yes, it's allowed to be 0 because it is allowed to be smaller than this, but it's not really 0 for most of the time, and its direction is a priori arbitrary. And is obtained from equations of motion. You have done this, I mean there are two blocks over each other and then one is sliding with respect to the other and so on. So you have done all those exercises several times. So n does not, in general, let's put it in general, n does not act at the centroid of contact area. See, the resultant force, there is a place where a resultant force acts, okay, and in general it does not act on the centroid of the contact area. So you should be able to verify this based on what you have learned earlier. Okay. You have learnt about how the resultant forces act on a line, on a surface, and a volume, and what point do they act through, and so on. So please go through that discussions and see whether this statement holds. Okay, so this equation, which is 2.62, which you can see over here, is valid for many situations. Okay, it's valid for idealized straight line contact if the direction and sense of tau is the same at all points. It is let me write that equation 2.62 is valid first for idealized straight line contact, if the direction and sense of tau is the same at all points. Secondly, it is valid for idealized point contact with curvature of one of the surfaces is 0. For idealized point contacts with the actually I should draw a diagram before. Let me do that over here. So you have this so this is clearly a fixed body, no slip. So you will have an n over here. So this is an idealized point contact between two rigid bodies. Okay. Similarly, you can have, say, there is a slip. So this is a rod which is contacted at this point, idealized as a point contact. Okay, in this case we're just moving with the velocity v, so we can write this as this D point is over here at the edge. Okay, this is the D point. So you will have a normal force, and then you will have a friction force, which is mu k into n. And you have, say again, it is impending slip. Okay. Oh. So this is the direction of this impending slip. Now you can show the friction. So on this contact point you will have N2, and the friction over here will act mu s N2. On this contact point we will have N1 and then mu s into N1. Okay, and you have the same point O, like this. So for idealized point of contact, okay, with the normal reaction n being in the direction of the normal to 1, okay, if radius of curvature of one of the surfaces is 0. Okay, or both surfaces of contact. So with normal reaction n being in the direction of the normal to 1 or both of the surfaces. So you can see and identify what are the cases in which the normal reaction is in the direction which is normal to one surface, and in some cases it is normal to both surfaces. Okay, I think this is where both surfaces there. Okay, now for a situation like this, in which there is a one-sided constraint, you can choose n greater than 0. Okay, but over here, which is a two-sided constraint, okay, this rod has constraint on two sides, you may not exactly know how friction acts. So in that way, just assume 1 and see if you get your value of n as non-negative. If it is, then then it's okay. If it does not, then you have to try again with n equal to 0 and sort of go ahead. Okay. So you can check some of these cases. I mean, the last case, which is also there in your text, perhaps I should do this. So you have, okay, and then you have so this is there, and then this goes up like this, and we get, sorry, okay, and then this. Okay, so I hope you get an idea of what this is. Now let me draw this sliding body over this. So this is the rod. So it is constrained to now move like this, and then you have this VP. Okay, so this is point P, this is A of this edge. Now if you draw this separately, you have to draw the MG, you have to draw, let's take the B one, which is easy. Let's draw the normal force, let's draw the frictional force, mu K N3. Now over here we'll have a normal force from this face first, okay, that must be drawn like this, and then the normal face will be from this face, that is N1, and the friction will clearly act in a way so as to oppose this motion along this edge. That would be equal to mu K into N1 square plus N2 square, which is the resultant normal force. Okay, so this is pretty much it. So you can see the more complicated cases of point forces as well. Okay, so let's take up another case, two cases of point contact. So please remember, it may not actually be a point contact, but it can be idealized as a point or a line contact. So what we are referring to over here is this case of idealized point contact. So a body makes contact at a point on a curved thin body, idealized as a curve C. Okay, an example can be a small bead on a wire. Let's see that with the diagram. So this is the curve C, and this is the bead which is in contact. So this, it will have a normal direction, it will have a tangential direction, and it will have a binormal direction, which will be essentially perpendicular to both of them. Okay, now in this case, if you want to show the friction forces, then say you have En, Et, and okay, so N2 AB and then F. Okay, so you will have this F as, I should actually show this without the sign because I've already shown with the arrow. So this will be minus F Et hat. This is the friction part, and N would be equal to N1 En hat plus N2 EB hat. Okay, so you will have N1. So the normal is in both the directions which are normal to friction. So this is where you can, how you can show the friction and the normal for this point contact on a curve. And the second case one can see is the a body makes point contact on a surface S of another body so say you have the surface S and then point P ET2, the second tangential direction. This is the first ET1 hat and this is the normal. Okay, so clearly this will be perpendicular. Now if you want to draw this, you will write it. So you will have the first friction in the ET2 direction, you will have the second friction in the ET1 direction, okay, and then you will have the normal in the n cap direction. So the friction force over here will be F1 ET1 hat plus F2 ET2 hat, okay, and the magnitude of F, needless to say, is F1 square plus F2 square, and the n will be equal to NEN hat. So for no slip we should have F1 square plus F2 square 1 by 2 smaller than mu s to n. Okay, just like for no slip over here, so no slip over here in this case we would have F is smaller than mu s into the magnitude of n, which is n1 square plus n2 square. Lastly, I mean, it's sort of an extension or a more realistic case. I mean, a merry-go-round, for example, for impending slip. Slip of a small coin on a disc say this is the axis, okay, omega dot, and then this is the coin. So this has the ER direction, this has a E5 direction. Okay, in this case if you look at the poor coin, it will have a normal force like this, it will have mg, its weight, so it will have minus F1 ER and it will have F2 E5 hat. Okay, for impending slip of a small coin on a disc rotating about a fixed vertical axis with angular acceleration Okay, so the friction components will be in the radial direction and the circumferential direction, this phi 1. So clearly the force of friction, this is the impending slip case. Okay, this will be F1 square plus F2 square, and this will be equal to mu Sn because it's an impending slip situation. Okay, now if we consider the other situation, which is of a rolling friction, so here we will have say it's a wheel which is, okay, I missed the contact. Okay, so this is at point B, this angle is alpha. So consider the wheel resting in equilibrium. Recall what equilibrium was, please check the definition. On an inclined plane of small inclination. Alpha not equal to 0. So we can draw its free body diagram, though we have not really discussed this word, but you must already be aware what a free body diagram is. So O is the center, B is this point of contact, and we are assuming a line contact. Okay, so you will have a normal force, you will have a frictional force. So this direction can be I hat, this direction can be J hat. Okay, and obviously the weight of it will act at the center of mass. This angle will also be alpha. The claim which we want to make over here is this: there do not exist any values of f and n which can satisfy fx equal to 0, fy equal to 0, and moz is equal to 0. So let's see what this means. So f is equal to w sine alpha. By looking at this you can say that n is equal to w cos alpha, and rf is equal to 0. No matter how small alpha is, okay, but alpha is not allowed to be equal to 0. Okay, so no matter how small alpha is and how large mu is, the wheel should roll. Okay, so the wheel resting in equilibrium on an inclined plane of small inclination alpha not equal to 0. So if you assume a line contact, this is a free body diagram which you would get, and we can say that there do not exist any value of f and n which can satisfy fx is equal to 0, fy is equal to 0, and moz is equal to 0. Okay, just because unless this alpha is exactly equal to 0, only then you can have fx and fy equal to 0. Okay, so that's the problem over here. But we cannot have alpha tending to 0, and the weight is clearly cannot be 0. So the only way fx and fy is equal to 0 is that alpha is equal to 0, which is not allowed. So that is why we are saying that there do not exist any values of f and n which can satisfy this. Now the next claim is no matter how small alpha is and how large mu is, the wheel should roll. Okay, so equilibrium will not be there. So what we wanted to start, so this was the equilibrium, right? This was the force balance which we were doing, and because we were considering something, the wheel was in equilibrium, but it turns out that the wheel will roll based on what we have just seen. But this contradicts our experience, okay, because in our real life we have seen cylinders being kept on an inclined plane and they are in equilibrium. Okay, so what is the conclusion out of it? Our modeling of this situation with a line contact is not correct. Because in real cases meaning this our experience, in real cases bodies are deformable and hence not strictly rigid. Okay, so in that case they have a small surface area of contact. So if you draw this over B, the force distribution will look like this. Okay, sorry, the force distribution say can look like this. This is a point B, this is O. Now this can be seen as a normal force and then a frictional force. So this normal force has a distribution like this. The normal force has a distribution like this and the friction force is shown. Okay. If the body, sorry, if the body tends to roll in the x direction, X direction is already given, I think, over here. Okay, this I direction, X direction is along I. Then deformation and contact force. Distribution on this side is larger than the other. So what happens is that then this will actually be more on this side, which is A, okay, compared to somewhere over here, which is C. So over A you will have more forces acting, just because it is trying to roll down in this particular direction. So the resultant normal force N does not act at an ideal point of contact B, but acts at a point A which is at a distance E ahead of B. Okay, so this distance is E ahead of B. Let me draw that properly over here. So this is the point B, this is the point F, and this is the point A. So the normal, so this normal is now the resultant of this distribution, and the resultant of this distribution was not acting at B, but it was acting at A. Okay, so this distance is E, and nothing else actually changes at O. W acts. Okay, so you can now draw a equivalent, and let's say that well, F remains as it is. N is allowed to act at the same point B, provided you have this additional MF equal to En. Okay, and then W acts as it is, and so on. So this is equivalent to this. Okay, equivalent force system. MF over here is called moment of, and this I should let you verify. Okay, please verify that these are two equivalent. The moment of rolling resistance. So for this situation, Fx equal to 0, Fy equal to 0, Moz is equal to 0 will now give and now meaning this one, okay, will now give F, N and E. So F will be equal to W sine alpha, just to tell you that this angle is alpha. N is equal to W cos alpha, and RF is equal to N1 MF, sorry. Equal to MF. Okay, so this is all about O, and this would mean that E is equal to MF by N or RF by N or R tan alpha. Now it is the experiments of this, what we have just discussed, show that the wheel remains at rest only for small values of alpha. Okay, that is, this E is called eccentricity. The eccentricity E of n has an upper limit, so has upper limit, that is E is smaller than equal to E1, and MF is smaller than equal to, hold on, E1n. Okay, this is called the inequality of rolling resistance. And E1 is called the length of rolling resistance. So called coefficient of rolling friction. So it has the, just by looking at this, okay, you can say that it has the dimension. Just by looking at this, you can say that it has the dimensions of length. Okay, E1 has the dimensions of length, since the dimensions of E1 and E have to be the same, and it may depend on the curvature of the contacting curves, speed of travel, and properties of the material and surface, and so on. Okay, and so in case of impending and actual rolling motion, the inequality of rolling resistance over here, okay, is replaced by the equality. Okay, it's replaced by equality of the rolling resistance, where this, so ME will become equal to E1 and MF will be equal to E1N. Okay, and so this is the axiom of rolling resistance. So I'll just put the last statement: in case of an impending and actual rolling motion, the inequality of rolling resistance is replaced by equality rolling resistance. Okay, so this is the axiom of rolling resistance. So if a body tends to roll over another body, like the case which you have seen, then the resultant normal force N acts through a point at a distance E ahead of the ideal line or point of contact in the direction in which impending or actual subsequent contact occurs. So for no rolling, E will be smaller than E1, and for impending or actual rolling, E is equal to E1. Okay, so E1 has its value, say for steel in ball bearings, as a 0.0005 to 0.0013 centimeters. Okay, for wood on wood, remember you have to have two surfaces. So for wood on wood, it is between 0.05 to 0.08 centimeter and so on. So for the case we have just discussed, the wheel, this figure, okay. For this situation now, since we now know for all the situations, we will have 1 F by N is equal to tan alpha smaller than mu S for no slip, okay, and E is equal to mf by N is equal to R tan alpha smaller than E1 for no rolling. If both are satisfied, if both of the above are satisfied, then it remains at rest. Okay, so remember we started off by assuming that this will be enough, but that's not true. So both of these have to be satisfied, no slip and no rolling to happen. Now if alpha is gradually increased, then slipping begins at what alpha is equal to tan inverse mu s if mu s is smaller than E1 by R, and starts to roll at alpha is equal to tan inverse E1 by R. Okay, you take this one, there you take this one. So then this limiting case, this inequality gets converted to equality. If E1 by R is smaller than mu s. Okay, so with this we can end our discussion on rolling friction.